Hi everyone, welcome back to Budget Power Electrical Solutions. Today we're continuing our Overload Relay series, and we're going to connect a few very important things together. We're going to talk about trip class, class 10, class 20 and class 30, motor starting time, and motor service factor. You may look at an overload relay and know how to adjust the current dial, but there's another important question. How fast should this overload relay actually trip? And when we look at the motor nameplate, you may also see something like service factor 1.15. So what does that mean? And does it change how we set the overload? Instead of making this just theory, we're going to use practical examples and see how these numbers affect a real motor installation. Alright, let's get started. Before we continue, just a very quick reminder about our overload relay. We've already covered most of these parts in the previous episodes. We have our current adjustment dial, our test and reset functions, auxiliary contacts, and the three-phase current path going through the overload relay to the motor. But today, remember just one important point. Current setting and trip class are not the same thing. The current setting is related to how much motor current we're protecting. Trip class is related to how quickly that overload relay responds under an overload condition. Keep that difference in mind, because now everything becomes much easier. Okay, so what exactly is trip class? Let's make it really simple. Imagine, I have three overload relays in front of me. Class 10, Class 20 and Class 30. They can all provide overload protection, but their response characteristics are different. Class 10 responds faster. Class 20 allows more time. And Class 30 allows even more time under the specified test conditions. Now you might ask, why don't we just use the fastest one? Wouldn't that protect the motor better? Not necessarily. Because when we start a motor, the current can be very high for a short period while that motor is accelerating. So our overload protection has to distinguish between a normal motor start and an abnormal overload condition. That is the real purpose of understanding trip class. Now let's use an actual number. Suppose our overload relay is set at 20 amps. For the NEMA trip class reference we're discussing here, we use approximately 6 times the current setting. So, 20 amps multiplied by 6 gives us about 120 amps. This reference helps us compare the response of different trip classes. A Class 10 device responds faster than a Class 20, and a Class 20 responds faster than a Class 30 under the appropriate reference conditions. But here's something I really want you to remember. Class 20 does not mean the relay always trips exactly after 20 seconds. This is not a simple 20-second timer. The actual trip time changes depending on how much current is flowing, the thermal condition of the relay, and the characteristics of that particular product. That's why, in real work, the manufacturer's trip curve is very important. Now let's look at the IEC side. Here you may see a different reference condition. For the example we're using, the IEC trip class reference includes 7.2 times the relay setting current. So using our same 20 amp example, 20 multiplied by 7.2 gives us approximately 144 amps. Now, don't worry about trying to memorize every number. The important point is this. NEMA and IEC don't necessarily define or test trip class in exactly the same way. So when you're working with an actual overload relay, check what standard the manufacturer is using. Look at the trip class printed in the documentation, and especially look at the manufacturer's time current curve. Don't take information from one type of relay and automatically apply it to every other relay. Alright, now let's forget the definitions for a moment. Imagine we're actually standing beside the machine. We have a motor with a full load current of 20 amps. We press start. The contactor closes, the motor begins accelerating, and let's say this machine normally takes about 12 seconds to reach its operating speed. Now we have a practical question. Class 10, Class 20 or Class 30, which one should we use? If we select a trip class that responds too quickly for the normal starting condition, the overload relay may trip before the motor has finished accelerating. The motor may be completely healthy. The problem could simply be that our overload protection doesn't match the starting characteristics of the machine. For the example shown here, Class 20 gives us a more suitable practical choice for this starting condition. And notice something important. We're not choosing Class 20 because the motor is 20 amps. We're considering how long the motor takes to start and what type of load it's driving. So, if I'm standing in front of a real machine, how would I approach this? I wouldn't just look at the motor horsepower and guess. First, I want to know the motor full load current. Then I want to know, how long does this motor normally take to accelerate? What type of machine is connected to it? Is this a pump that starts fairly easily? Or maybe a large fan, conveyor, crusher, or another high inertia load that needs more time to accelerate? And then I check the manufacturer's recommendation. So this is a good way to remember it. Motor FLA helps us determine the overload current setting. Motor starting characteristics help us determine the appropriate trip class. Those are connected, but they're not the same thing. Now let's bring in another number that you may see on the motor nameplate. Service factor. For example, you may see SF 1.15. So what does that actually mean? In simple terms, service factor is information from the motor manufacturer about the motor's allowable operating capability under the specified conditions. Now let's take a simple example. Suppose our motor full load current is 20 amps, and the service factor is 1.15. If we multiply 20 times 1.15, we get 23 amps. But here's where I want you to be careful. Please don't look at that and say, okay, my motor is 20 amps, service factor is 1.15, so I'll automatically set every overload relay to 23 amps. That's not the correct way to approach every installation. The actual overload setting has to follow the applicable requirements, motor information, and overload relay manufacturer's instructions. The first practical habit is very simple. Read the motor nameplate before touching the overload dial. Let's put some numbers into this example. Our motor FLA is 60 amps, and the service factor shown is 1.15. So the simple calculation illustrated here is 60 multiplied by 1.15, which gives us approximately 69 amps. Now this is where practical thinking becomes important. Don't stop at the calculation. The next question is, does my overload relay have an adjustment range that includes the required setting? If it does, then we can make the appropriate adjustment according to the applicable requirements and manufacturer's information. After we start the motor, we check the actual running current. Let's say the motor is supposed to operate around its expected load current, but instead we're seeing unusually high current on one phase, or on all three phases. I'm not going straight back to the overload dial and turning it higher. I'm going to ask, why is this motor drawing that current? That's real troubleshooting. Alright, let's bring everything together. Today we learned that trip class and overload current setting are two different things. Trip class is related to the response characteristic of the overload relay. Class 10 is faster than Class 20, and Class 20 is faster than Class 30 under their specified conditions. But choosing the correct class also means understanding the motor's normal starting time and the mechanical load. We also looked at service factor. Service factor is motor nameplate information, and we need to use it correctly, not simply multiply a number and automatically turn the overload dial higher. So when you're working with an overload relay, look at the whole application. Motor FLA. Service factor. Starting time. Trip class. Relay range. Manufacturer information. And finally, the actual measured motor current. That's how we move from theory into practical motor protection. Thanks for watching Budget Power Electrical Solutions. And in our next episode, we'll look at something very useful, the overload relay time current curve, and I'll show you how to read that curve in a practical way. I'll see you in the next one. Hi everyone, welcome back to Budget Power Electrical Solutions.